All right, we're just going to look at a couple other criteria that could help you determine whether or not a sequence converges. And then we're going to also look at one thing that tells you what happens to sequences if they do converge. And so first of all, we have this theorem right here, which tells you that bounded monotonic sequences converge. And so first of all, bounded is hopefully a term that you've seen before. It just means that a sequence can't go off to infinity in either direction. Or in other words, it must be stuck between two finite values. And then monotonic is just a fancy word that means either increasing all the time or decreasing all the time. And so it can't increase some of the time and then decrease. It can't decrease some of the time and then increase. It's got to do one or the other. And so as a quick but pretty simple example, let's look at a sub n is equal to 1 minus 1 over n. And so if I sketch a graph of this sequence, then overall it's going to look like an increasing list of numbers. And as I plug in values for n equals 1, it's going to be 0. And then for n equals 2, it's going to end up being 1/2. And it will keep on increasing like this. But we can see that it's never going to go above the line 1 here, and that's because we're always subtracting something off from 1. And so because this is increasing, a sub n is monotonic, and because it never goes above the line 1, and it also never goes below the line 0, it's also bounded. And so this theorem then tells me that a sub n converges. Right? So it does not tell me what a sub n converges to, but it does tell me that it converges to something. Of course, in this example, we could have just taken the limit to begin with and seen that the limit was equal to 1. But this is just an example for how you would check the criteria for this theorem. All right, so now let's look at a non-example. And so this sequence we've already seen before, b sub n is equal to sine of n over n. But if I draw a graph of this sequence, which again, this is going to be a really rough sketch that's not exactly what the sequence looks like, but it's close enough, then we're going to get something that sort of follows a sine curve, but overall it's going to get closer and closer to 0. And so it is the case that this sequence ends up converging, but b sub n is not monotonic. And it's not monotonic because it keeps on changing directions here. And so that means that the theorem doesn't work here. But we already saw how to deal with this particular case, and we could just use the squeeze theorem. And so the reason why the squeeze theorem works here is because the squeeze theorem is really good at handling things that oscillate. Right? And so this particular theorem that we're talking about right now talks about things that do not oscillate because they're either always increasing or always decreasing. And then on the other hand, the squeeze theorem tells us how to handle things that do oscillate. All right, so now we're going to flip things around a little bit and see what can we tell about a sequence if we do know that it does converge. And so that's what this theorem down here tells us, and it says that a convergent sequence must be bounded. And so first of all, you'll notice that that's not exactly the same phrasing as the first theorem on this page. So here, the only thing that we learn is that a convergent sequence is bounded. It does not need to be monotonic. And so let's look at what this theorem might help us show. And so if we look at this example right here, where c sub n is equal to n times sine of n, if I do a really rough sketch of this again, it's roughly going to follow the sine curve overall, except as I go further out into the sequence, it's going to get larger and larger and larger because of that n out front. And so that means that c sub n is not a bounded sequence. But from this theorem, we know that all convergent sequences are bounded. And so that means that if c sub n is not bounded, that implies right away that c sub n does not converge. And so that's sort of a backwards way of using this theorem, but it is an important thing that we could look at for sequences that do not converge. On the other hand, we can look at this non-example right here where the theorem is not going to be useful, and that example is if we just look at the sequence sine of n. And so if I do a rough sketch of this sequence overall, then we're going to get something that looks like it's following the sine curve like usual. And it's pretty clear that this sequence is bounded. However, it's not monotonic, and so the theorem at the top of the page does not apply. And also, it doesn't converge. And that's just because it oscillates forever. And so the point here is that we have to be really careful about these sequence statements, because the fact that a sequence is bounded is not enough to show that it converges, because some of the time it's bounded but it oscillates, and so it does not converge. And so the only time that we know that a sequence converges with these criteria is if it's both bounded and monotonic. Or if we know that a sequence does converge, then we do know that it must be bounded.